This is Module 10, and this video will start Exploration 4.2. See the next video for continuation. So it says, an area of research in biomechanics and gerontology concerns fall and fall-related injuries, especially for elderly people. Recent studies have focused on how individuals respond to large postural disturbances like tripping or induced slips. One question is whether subjects can be instructed to improve their recovery from such disturbances. So suppose researchers want to compare two such recovery strategies: lowering, where they quickly step down with their front leg and then raise their back leg over the object, or elevating, lifting their front leg over the object. So basically here they're saying that they just have these two strategies, like called a lowering strategy, and the second is called the elevating strategy. Just when they trip, they teach them one of the two strategies and they're trying to see if one of these strategies helps them from hurting themselves when they fall. So subjects will have first been trained on one of these two recovery strategies, and they'll be asked to apply it after they feel themselves tripping. The researchers then induce the subject to trip, but they are harnessed in for safety, and then they used concealed mechanical obstacles to actually trip them. So suppose the following 24 subjects have agreed to participate in this study. Notice there are 8 females, and notice there are 16 males for a total of 24 people. Question 1 reads, one way to design this study would be to assign the 8 females to the elevating strategy and then assign the 16 males to the lowering strategy. Would this be reasonable? Why or why not? So notice, as we discussed in our previous videos in this module, this would not be a good strategy because you would really purposefully be introducing a confounding variable. If we did it that way, then if we found that the elevating strategy people did better, for example, then we couldn't say that it was the fact that they were using the elevating strategy that made them do better. It could be the fact that they were female that made them do better. So that gender would have been a confounding variable. It would not allow us to say that the strategy itself is causing the difference. Question 2. One way to deal with this issue is to assign 4 females and 8 males to each group. Show how the proportion of males in each group would be the same. So notice, if you had 4 females and 8 males in the elevating group, then there would be 12 people total in the group. There'd be 4 females in the group, which would be 33% females in the elevating group. Similarly, the other group, the lowering group using the lowering strategy, would also have 4 females out of 12 total people, which would be 33% females. Notice then that means if you assigned females and males to the two groups in this way, they would be balanced by gender. And that's good. We do want them to be balanced by gender. Part 3 says, now if you saw a difference in the proportion of the trips in the two groups, could it be attributed to the sex of the subject, the gender of the subject? Why or why not? So now if there were a difference in success between the two groups, it could not be due to gender, since gender is balanced between the two groups, 33% females in both groups. It does ask, though, could it be due to other variables? Well, yes. For example, maybe all the tall people are in the elevating group and all the short people are in the lowering group. Or maybe all the people in the elevating group have a special gene that makes them have better balance. It could be the case that one of the groups has some trait that makes them better than the other group. So, number 4. Because there are always going to be potential confounding variables which could be distributed unevenly between the groups being compared, identify a better method for deciding who uses which strategy. So a better method for assigning people to the two groups and deciding, which thing you're going to do, elevating versus lowering, is random assignment. if we just randomly, like drawing from a hat basically, if we randomly assign everybody to the two different groups, then I will probably not end up with like all females in one group and all males in the other. If I randomly assign people to groups, it's very unlikely I would end up with all the tall people in one group and all the short people in the other group. If I randomly assign people to the two groups, it's very unlikely that I would end up with all the people with a certain balance gene in one group and all the people without that gene in the other group. So number 5, let's explore that process of random assignment to determine whether it works. First, let's focus on sex, gender, male versus female. So suppose we put each person's name on a slip of paper, we put all the slips in a hat, we mix them up thoroughly, and we draw out 12 slips for the names of the people who are being assigned to the elevating strategy. So notice that's really randomly assigning people to the elevating strategy group. What proportion of this group would we expect to be male? Well, if we randomly assigned them, remember at the beginning of this problem, we said there are 16 males out of 24 total. So if you're randomly assigning people to groups, I would expect that that is the ratio of males you would see in each group. So I expect approximately 16/24 of them to be male. If we simplify that down, that's 2/3 of the group to be male. Notice what that means then, since we're assigning 12 people, so we expect about 8 males in the group of 12. Notice that would tell me maybe 7, 8, 9 would be normal, maybe even 6, 7, 8, 9, 10 would be normal. We need to look at the distribution of sample statistics to see what is normal, usual, and expected. But certainly 7, 8, 9 would be normal, usual, and expected if we're saying about 2/3.